So indeed, today we'll be talking about what really lets ChatGPT work. So this kind of serves as a summary of what we've talked about so far and kind of explain some possible future directions. So we'll kind of cover again the idea that language is maybe, in a sense, simpler than it seems. We'll talk about the idea of meaning space, like we talked about embeddings yesterday. So we'll kind of expand on that a little bit about possible future directions for understanding language and LLMs both. We'll talk about how language is used to describe real and possible worlds and what the possible differences between these things might be in the context of generative AI. And we'll kind of give a high-level summary of what ChatGPT is doing and why it works, and then suggest directions for future exploration. One of those directions is integration with computational languages like Wolfram Alpha, which will be the focus of tomorrow's talk by Alan Joyce, who is the manager of socioeconomic content on Wolfram Alpha. Okay, so remember last time we learned about embeddings, which are ways to represent arbitrary inputs in a big space of numbers. For example, these digits live in a 10-dimensional space where each dimension corresponds to some digitness, zeroness, oneness, two-ness, and so on. And we don't know what exactly those mean, but we do know that they are meaningful because, as you can see, these fours all have a really big fourness and they don't have very big anything else. And these eights have a really big eightness and they don't have a really big anything else. And these two eights are similar and these four fours are similar. So this is a meaningful way to talk about things. We learned that the transformer architecture has attention blocks, which allow the network to look at its input, break it into little pieces, reweight the pieces, and then multiply them by a big matrix. And despite that being all, a weird mathematical thing, what this is fundamentally doing is it's learning about some of the possible structures of language. In ChatGPT's case, primarily English, although, it also has some knowledge about how to do various types of coding, as you've probably seen. But the idea is, this could detect how maybe nouns and adjectives relate to each other, or how noun-adjective pairs relate to verbs, or how those verbs relate to, their subjects and objects, and things like this. We also learned that the kind of default output of the training process is statistically human, but it doesn't pass the smell test. So you need human reviewers to kind of score the outputs. Then a new neural network is trained on those scores, and it's used as a loss function. So now you train the network a little more, and whenever it behaves badly, you have a neural net that acts like a human reviewer saying, bad, bad, don't do that. And then it says, oh, okay, sorry, I will not do that. I will go ahead and produce more human-like text. Thank you very much. And then the final thing we talked about yesterday was the idea that there are things that neural nets and LLMs in particular are not so good at, particularly things that involve a lot of algorithmic steps or things that involve computational irreducibility. That is, computations that don't have like a nice shortcut from beginning to end. So we noted that just like people who are also pretty bad at these things, if you give the LLM access to a tool like Wolfram language, then that kind of covers up a big fundamental hole in the functionality of the LLM. So in brief here, we think about the human brain as kind of the pinnacle of complexity, and I think there's good reason to do that. And all the stuff it does through about 100 billion neurons with maybe about 1,000 connections per neuron on average. So I think in a sense, it's a little surprising that this much complexity could come from only 100 billion little objects, and they really just have little voltages that move across them, right? So maybe it makes you think, maybe there's something more going on in the brain than, 100 billion little electrical guys sending signals back and forth. Maybe there's something more mechanically complex going on. Well, LLMs like ChatGPT give us some sense that maybe maybe that really is enough to do what the human brain does. Because a purely artificial, super simplified network like this, because fundamentally this is really what ChatGPT is doing. So numbers come in, those numbers get spread out to other neurons with some weights. Those get combined and sent to the next layer, and so on and so on and so on. And this actually does seem to do a pretty good job of reproducing human language. And it does it with about the number of neurons, about the number of connections that the human brain has neurons. So it seems like, if you have that number of neurons, probably you can get some pretty complex behavior. And it is certainly the case. We don't want to kind of lose sight of the fact that a system with a few 100 billion or a few trillion connections or weights or parameters, we don't want to say that that's not complicated, but want to really reiterate here that the underlying structure is simple. Some text goes in, it gets converted to a bunch of numbers. Those numbers then just get repeatedly multiplied by some other numbers and added up. And then at the end, the final number is converted back to some text. And that's really it. The actual fundamental math operations of the thing are quite low level. So part of the explanation for this, you'll always see a cellular automaton in a Wolfram course. Part of the explanation is that you can have simple computational rules that result in something that appears to be quite complex. A famous example being the Rule 30 cellular automaton. Now, this thing, this looks kind of crazy, right? It's got all these triangular structures just kind of appearing and disappearing in a way that looks random, and it's got like structure on the left side, but then on the right side, it's kind of crazy. This is a very strange object. So no wonder that it's kind of an interesting thing to study. But the governing behavior of this apparently complex object really is quite simple. Here are the rules. That's it. So you start from a field of white squares with one black square in the middle. And then the rules to color in the next row is you go to the next row and you just look up. Just look up at the one row before you. If you've got 3 black squares, you turn white. If you have 2 black squares in this order and then a white one, then you get a white square, and so on. So you just look at the 3 neighbors above you, and the color and order of those 3 neighbors totally determines what color you get. And so just by using these rules, there are only 8 little rules here, and each one only has 4 binary pieces of information, then if you have that, that's enough to generate something like this. So rather simple rules, rather simple systems can generate rather complex behavior, is the idea. So not only are these rules enough to create the intricate structure you see above, but you have to use those rules to compute the structure above. There's no shortcut like we talked about. You might remember again that this is different from the kinematics example, where you don't need to go through every step. You don't need to compute every step along the way. You can just say, if you give me an initial angle and you give me an initial speed and you tell me the time, I'll tell you where the ball is in the future. And that's it. You don't need to go through every step. Like we don't need to go through and compute this and then this and then this and then this and then this and so on. Whereas up here, we do have to compute this and then this. Also, recall we mentioned that these neural nets, transformers in particular, are constructed to avoid going too much into this idea of computational complexity or irreducibility here, because there's nothing to learn. It can't learn, say here, you could learn the rule and say, oh, okay, the position is given by, x is equal to 1/2 at squared plus v naught t plus x naught. There's no rule like that to learn. Instead, there's what winds up happening is that it starts memorizing what all the lines of a cellular automaton would be if you ask it to try and reproduce it. So it doesn't learn, it memorizes. And we want to avoid that because not only is it just kind of a bad behavior for a net to do, but it's also really inefficient. So you don't want your net to do that. So kind of the takeaway here is that maybe, ChatGPT actually works because language is maybe not as complicated as we might have thought it was. Um, ChatGPT has this ultimately straightforward neural net structure. Again, it's numbers and then a bunch of matrix multiplication. It's a lot of numbers and a lot of matrix multiplication, but it still is just those things. It seems to be able to capture whatever it is that makes language feel like language. And maybe this could imply that there are some ultimately simpler laws that dictate what linguistic constructions are possible, kind of like the laws of kinematics tell us what's possible in terms of like throwing a ball or what have you. But if these laws do exist, they are implicitly represented in the neural net architecture of LLMs like ChatGPT. That is kind of a big if, but this is just about possible future directions. So if they do exist, they'd be represented implicitly. So remember when we had the net learn this function here, inside the net, there's nothing that is like explicitly in these neurons that says, oh, it's a step function, and the step function has this value from here to here, and then it jumps to this value from here to here, and then it goes back down to this value from here to here. There's no explicit mention of the law in the network, but nevertheless, it has implicitly learned the law that generates this function. And the idea is, it's possible that something like that is happening with language. Maybe we can't go in there and pull out laws of language, but maybe it has implicitly learned laws that can generate these things. And so maybe there are some explicit representations of these laws. It's unclear. So if we think about laws in terms of language, the first thing we probably think of, at least it's the first thing I think of, is just the ideas of syntax. And that tells you about how words can fit together in order to form a proper sentence, right? So you can take a sentence here. The best thing about AI is its ability to learn from experience, the sentence that keeps popping up in this book and thus this study group. And we can see that each thing has its own, you can group these things into pieces, into sub-pieces with labels, parts of speech, and then this kind of explains how the sentence is allowed to fit together. So these rules, like we could enumerate the rules of syntax. Those are, rules you learn in, well, depending on the level, but I think typically we kind of learn these things in elementary school, right? But these rules, as such, they're not stored in ChatGPT, but it has figured them out in the implicit sense. So how does it manage to do this? Well, let's take a simpler example, as we are often wont to do with complex systems such as these. So imagine a language that is made up only of parentheses, and the only syntactic rule is that every opening parenthesis must eventually be closed. That's it. That's the language. So the question is, can a transformer like the one at the heart of ChatGPT, so that is a GPT 234 or whatever it might be, network, can that learn this rule if it's fed a bunch of examples with correct parentheses matching? The training does converge, and you don't need such a complicated net in order to generate a net where the training does converge, but let's see what we get. So let's say we start with these 3 opening parentheses, we close one of them, we open and close another one, then we open one. So what comes next? Well, we really need to close this parenthesis, I think, but it's possible we could keep going, right? But what's important to note here is that the model is pretty sure that it can't end here, which is true, because if it ends here and it just puts, imagine it puts a period at the end and that's the end of the quote unquote sentence, we would have a mismatched or unbalanced number of parentheses. So it's good that it thinks it really is unlikely to be able to end there. But in the second one, let's have a look again. We open, 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 close, open, close, close, close. So this is already balanced. So this is saying, well, what could we do here? The most likely thing is we could open up a new parenthesis. That would be nice. We could just keep the sentence going. The next most likely thing is that we could end it, but it still thinks with the 15% probability that maybe it could put a closing parenthesis here, and that can't work because there's not an open one to match it with. And if you put that, the whole thing is automatically going to be wrong. So this transformer model even though it does converge when you teach it, it does, flatten out and reach a minimum in the loss function. It still thinks that there's a 15% chance of doing something that's illegal, even though there's only one rule about what's legal and illegal in this type of imaginary language. So that's a little bit too high for our comfort. So we could kind of go through here and we can kind of start to see the problem. The gray are kind of our input text, our input prompts, so to speak. And then the black ones here are the predictions for the network about what's the most likely thing to come next. So you can think of this as the temperature 0 setting of the parentheses GPT. So you go through, and for the shorter ones, the most likely option it picks is pretty much right. It picks a good idea. But as you get longer, you start to see more and more cases where it kind of loses track of what it's doing, and it starts to give you unbalanced results. And this is not infrequent with neural nets. We can, as people, we can kind of quickly internalize the relevant rule. We can learn things like that, and we can just see that an example is right or wrong. But neural nets are usually not quite as good with these sort of directly algorithmic tasks. So the thing about real languages is that while they are much more complex, they are a little bit less directly algorithmic. So if you look at a sentence, there are lots of different pieces of the sentence that all fit together just so. You might think, if you've had a Latin class back in the day, maybe, you might think about how in Latin you have conjugation and declension, and a lot of it might seem kind of redundant, right? Like, oh, well, I already knew that this was going to be the subject of the sentence. Just like in English, most words don't have a declension. You can just kind of tell what the subject is and what the object is and so on without having to change the ending for it. So there's a lot of redundancy in Latin compared to English. That redundancy often gets filtered out over time from languages. But the thing is that redundancy helps people to learn, what a subject is and what an object is and what an adjective is and what goes with what. It reduces the ability to mess up. And so real language, unlike the parentheses language, has a lot more kind of built-in redundancy, and there's a lot more complex relationship between the parts of these sentences than here. So this simple rule of close any parentheses you open is a little bit harder to learn for a transformer than more complicated rules about how English words should fit together, just because there are more hints in this English sentences than there are in here. And, it's worth thinking about, and I think this is relevant for ChatGPT, right? You can think of a syntactically correct sentence that makes no logical sense. The massless cat ate sentences for lawns. Like, that is an allowed sentence according to the syntax rules we know. But generally speaking, it has flubs every now and then, but so do we as people again. But generally speaking, ChatGPT does not do this. So in addition to learning some syntax, and it has learned some sense of logic about what things are logically allowed to fit together, even though, again, it doesn't have concrete rules for logic that are built in. So it has some implicit understanding of both syntax and logic. And this suggests, again, maybe, that there might be some laws of language that just don't yet have a nice or human readable form, since ChatGPT does have an implicit understanding of these things. Before we move on, let me ask a few questions here. The first question is, which of the following tasks are neural nets not particularly good at? Algorithmic computations, sound recognition, speech generation, and image identification. And mentally anticipating this poll question that I wrote, I have really hammered home the exact answer repeatedly while talking about this slide. I said it's kind of one of the fundamental points of today's lecture, though, so can't feel too bad about it. Okay, we have about 86% of people saying algorithmic computations, and indeed, that is true. The next most popular answer, with about 10%, was sound recognition. And it's actually really good. Neural nets are really, really, really good at sound recognition, especially compared to traditional means. I mean, there are many examples, but like modern speech to text that you use, in addition to text to speech, it's basically all neural net powered. And it was found that these things are just much better than traditional methods. They're also, in a lot of cases, faster, although the models tend to be a little bit bigger. This isn't so much a problem when you have a lot of space available, though, right? The same thing goes for kind of other neural net powered things like text to speech, the reverse process. But it's also good for, just a quick example. This is a feature I liked when I was on Pixel. They had a feature called Now Playing, where if there's music playing, it will show you what the title of the track is on the lock screen. And the way it does this is every minute it turns on the microphone. Scary. Every minute it turns on the microphone and it listens, and it has a special neural net that's been trained to say, is music playing, basically. Listen to sound and determine, is that music playing or is that just like normal talking or what's going on? And then if it determines that it's music, it has kind of a local, storage of, or a local database, I should say, of like the top, several thousand most popular songs at the time, plus some other, classics and stuff. And it has converted those into little embedding snippets. And then it just compares what it's hearing after determining that it heard a song to the embedding snippets. It's a little more complicated because it has to deal with background noise and stuff. But it's able to kind of filter out the background noise and compare directly to these embeddings and then just tell you what the song is, which is pretty neat, honestly. You got to give it to them. It's a nice use of neural nets. And on that note of song embeddings, say, recall from yesterday this idea of an embedding. This is a way to describe a word or really any other input as a numerical vector. So this lets you imagine ideas as living in some kind of space. I got distracted by my pretty graphic and I forgot that I had another poll here. So quick one, just a true or false. ChatGPT has effectively learned laws, quote unquote, about syntax and semantics. Okay, looks like we have about an 86-14 split here in favor of true. And yes, it is true. I did put the laws part in quotes intentionally here, because it's not clear that some universal governing laws of syntax and semantics exist, but whether they do or whether they don't, ChatGPT has some implicit understanding of whatever it is that makes a sentence make syntactic sense, like kind of our classic syntax laws, and also logical or semantic sense. So generally it constructs sentences that are, reasonably well constructed English sentences that also make sense. So it has implicitly learned some of these laws. And there is a question here that's an interesting one: learned versus memorized versus stumbled upon. Yeah, I mean, that's a fair thing to talk about. Although I will say, as far as learned versus memorized, generally speaking, it is not memorized, these things. So if you look in the network, like the words and the possible sentences and stuff, these things are not stored in the network. In some cases, it has maybe overlearned a little bit, in which if you ask it a very, very particular question, it might give you an answer that is very exactly pulled from somewhere in its training data. If it doesn't have a way to kind of give you a reasonable, probabilistically generated answer, that can happen. So you might see snippets of stuff taken from other places in LLMs, which is an issue, certainly. But I do want to kind of push the point that inside the network, this is a bunch of connection weights. And those matrices that we saw yesterday do encode something about human language. It's not just memorizing possible outputs. But it is, I will admit, it is kind of a subtle thing to talk about there. Okay, so back to embeddings here. We had our embeddings for our colors. And so when ChatGPT thinks about words, a lot of operative quotes from me here, it's working with these high dimensional numerical vectors, and then it feeds them forward repeatedly through the layers of its network, a bunch of matrices. So if we project down into 2 dimensions, we can kind of think of a meaning space for some common nouns. We can see what things are kind of related to what other things in this concept space. It's a lot more crowded in 2 dimensions. You can imagine, you can have a big complicated 3D object, and then if you cast a shadow down from that 3D object, it might lose a lot of the details about what makes that 3D object have its particular shape, but you can recover some information from that shadow. And so here we get something a bit crowded, but we can see, relationship, relations. We have, text and words and language, things like this. Things go here: plaintiff, defendant, trial, committee, member, organization, movement, and so on. So it's grouping these things together in concept space, right? And if we have this example here that uses different parts of speech, we can kind of see some of the natural grouping that occurs in this space. So we've got these here, nouns, we've got verbs overlapping with adjectives and a bit with nouns. And then these adjectives fill out kind of this strange area here. And then adverbs are kind of off to themselves. Pronouns are off mostly to themselves, but some are here. And so on. So making kind of a rudimentary analogy to physics, to the kinematic laws that again govern the motion of a thrown ball. It's my kind of standard physics example here. It might be that there are laws that constrain how it's possible to move from point to point within this meaning space, if you want to make syntactic and logical sense. So here, if we follow that sentence we keep using, the best thing about AI, if we follow this thing around in meaning space, we have the best thing. We kind of go around in this pattern. And it might be that there's some sort of, there's some sort of kinematic-like law about how this thing should be allowed to move in order to make sense. So, there are all sorts of different formulations of classical mechanics, whether it's kind of Newtonian kinematics or like, Hamilton, Jacobi dynamics, or whatever other thing. There are all sorts of different underlying rules that you can use to rederive the motion of things through space. Now, looking at this, it's pretty clear, if you ask me, that there's no obvious law that you can derive by looking at this picture. It's also not clear what embedding space would be best to represent such a law, if such a law should exist. And that's a complicated story that you can read more about here from Stephen. So, just to indicate here, when we talk about an embedding space, it is a meaningful thing, but it might not be the right way to think about the meaning space. The embedding that we've chosen, it just happens to be good and it happens to work for our network. There's nothing fundamentally correct about that representation of words and ideas, right? So it might be that a different embedding space or a different basis in kind of the classical parlance might be a better way to talk about these laws of motion if they should exist. And now, that at each point here, when you have 2, there are different possibilities for what word comes next. And you can kind of think of these probabilities as little fans with vectors pointing out, in a bit of a fan. And it is interesting here to note that at least in this embedding space, these fans all kind of point in this direction for the most probable things. And you can look at each of the steps in turn, its ability to learn, ability to learn. You can kind of go on and follow these fans through and then trace out the actual path. And again, it's not clear from this. This looks pretty messy. And in 3D, if you put the fans in gray, this, instead of projecting our huge concept space into 2D, we're projecting it into 3D. And this just goes from word to word in that 3D space. And then once we get here, this is the end of our prompt. And then this here represents the path that ChatGPT is taking through meaning space, with all of the gray bits here being possible paths that could have been taken at each given step. And, it must be said, this really does look like a mess. And it doesn't look like that you can derive much in the way of any sort of semantic laws of motion by looking at these embeddings that ChatGPT is using or how it moved around in this embedding space. But it is worth noting on this front, keeping an open mind, that sometimes you just have to kind of tilt your head a certain way. That's what a favorite professor of mine, one Lorenzo Sedun, highly recommend his book, Applied Linear Algebra, the Decoupling Principle. No affiliation. He even uses MATLAB in the book. Can you believe it? But I really like the book. Very good book, especially for physicists. So sometimes if you tilt your head, which is how we would talk about changing bases, a certain way to make sense of something might appear out of something that looks messy. So if you don't know any calculus, probably this looks, well, I just gave away the game because of that zoom. Wow. This looks really messy, right? It's just this weird polynomial. It's got a weird bunch of numbers on the bottom. It goes plus, minus, plus, minus, plus, minus. It's a bunch of odd numbers. It's a weird thing, right? And you'd be forgiven for thinking that this also looks messy, right? These are two ugly, messy expressions. But if you look at them through a different lens, if you just plot them in particular, this first one, it's just, it's more or less sine of x. And the second one, it's just a modulated sine of x, despite all the complexity. So in the first case, we did a power series representation of sine of x. And, the right way, quote unquote, to think about the function is just as the trigonometric function we know and love. We think of sine of x as sine of x, as a wave. But there are a bunch of different ways that you can represent sine of x, including, a Taylor series representation that looks like this. And then there are more and more terms. In fact, there are infinitely many terms, with the numbers getting more ridiculous on the bottom as they come from factorials. But if you kind of, again, tilt your head, and instead of thinking in the basis of polynomials, you think about it in terms of what's natural for a wave, which is, say, a sinusoid, which we've defined to work that way, then it's all pretty. It's all nice. Everything's great. And the same thing goes for this guy here. This is a Fourier series expansion of just this function here, sine of x minus 2 sine pi squared of x. So in the Fourier space, you have to do this complicated thing where you add up a bunch of complex exponentials, and the constants in the front are determined by these integrals, these Fourier transform integrals. And there are similar examples of this all throughout the natural sciences. For any given phenomenon, there are a lot of different ways to talk about it. And it's often the case that one of the ways makes everything kind of click. It makes everything seem simple and clear. This is not to say that there are no uses for the other ways, of course. It's unbelievably useful to be able to break down, say, sine of x into a sum of polynomials. Physics would basically just not work, at least not the way we currently imagine physics working, if we couldn't take power series expansions. Everything is based on power series expansions because the simple fact of the matter is that most functions are too complicated to do lots of different analysis on. And similarly here, even if the embedding space that we've picked, or that has been picked for us, so to speak, for ChatGPT, isn't useful for discovering any possible semantic laws of motion, it is useful for generating human-like language. So that's something. But it might be possible that if we turn our heads, this could turn from something ugly and nonsensical into something that maybe has a bit of meaning, possibly. Okay, let me see if I have a poll for that one in particular. Yes, another simple true-false one, I hope. So the path ChatGPT takes through meaning space when constructing text clearly follows some semantic law of motion. Is that true or is it false? Okay, we have what in my view is a bit of a surprising result. We've got 2/3 saying false and 1/3 saying true. So again, just briefly here, the question boils down to, if you look at this, do you see a clear law that governs this motion? That's the kind of rephrasing of the poll question. So I would say no. This may, in another basis, be meaningful and may clearly follow some law. Maybe if you just draw this right, who knows? It's taking a big parabolic arc through meeting space, just like throwing a ball. I find that unlikely, but it could be something else that's not quite that simple, but at least more reasonable. But I would definitely not say that this clearly follows some sort of law of motion in meeting space. Okay. Let's move through. All right. So we've seen that ChatGPT can produce meaningful text, and it generally makes syntactic and even semantic sense. And it may be the case that there exists a fundamental set of laws about how sentences can be constructed in order to make both of those types of sense, syntactic and semantic. ChatGPT has certainly discovered some underlying laws implicitly, or it has an implicit understanding of the laws. So it might be the case that we could write simpler versions if these laws exist. So let's see here. The kind of idea is that, in an ideal world, it might be possible that we can take our kind of implicit representation and turn it into something explicit. Again, like the like this expression here, which, funnily enough, speak of power expansions. Note that this is 1 over, I wish that didn't happen. I broke my nice majiggy. Okay, but note that this is 1 over 2 factorial, and then this is the second derivative of x with respect to t, and then this is t squared. And then here, we've got the first derivative of x with respect to t times t to the 1 over 1 factorial. So even the basic laws of kinematics are a Taylor expansion of the position with respect to the time variable. So it never goes away. Everything's power expansions. But here we, ideally, we would hope that the fact that this works means that we can maybe find some sort of explicit representation of laws of syntax and semantics. And syntax, I think, is reasonably simple compared to semantics, of course. So, like I said, we kind of have these laws in mind about how sentences can be constructed syntactically from early childhood, generally speaking, or whenever it is you learn a particular language. But semantics, more complicated. There are all these different ideas that need fine classification. So if you think about what it means to move, for example, it means there's some object that remains fundamentally the same, and then, regardless of its location, it remains itself, and then the location of the thing changes, and that's moving. Or growing, where an object maintains its features, but the size gets scaled up. Or eating, this idea where one object, so to speak, consumes another and possibly breaks it down into constituent pieces, and there's all this other complex stuff going on. So in terms of semantics, things can get quite complicated. So, the cat moved from the living room to the kitchen. The ball moved from the ground to the air. There is something, related about these sentences, about what they're talking about semantically. And, we mentioned that a sentence could make semantic or syntactic sense, but not semantic sense, which was this massless cat eating sentences sentence. But it's also the case that a sentence could make syntactic and semantic sense, but it's still not something that's been realized in our world. Like this aped, perhaps, picture. I figure image synthesizer is a fun thing to use for a talk about LLMs or for a study group about LLMs. But it could be the case that you could write a sentence, of course, that makes sense syntactically and semantically, but is not something that describes something about the real world, right? So if you want to have a semantic grammar, ideally it should have a sense of what's actually possible and what's been achieved beyond like making theoretical sense. Like an elephant could travel to the moon in theory, but it seems pretty unlikely, right? So ideally, if you have a semantic grammar, it should have a model of the world that it is attempting to describe. So one of those models might be the model of our world, where certain things are possible and other things are not possible. Some things have not happened yet, some things are unlikely to happen, and so on. If you wanted to have a semantic grammar for, say, a book or a movie, those things could be very different, right? So ideally, semantic grammar, an LLM, a language, should all have a sense of context. They should know what world it is they are trying to talk about. And if you've used Wolfram language much at all, especially if you use Wolfram Alpha, you might think that this sounds a little bit familiar. So we've been kind of working on making it so that our language has an awareness about the world for quite some time now. So the idea then is to get a computational language that has knowledge about the world and precise symbolic ways to talk about the world. So Wolfram language, as kind of a budding example of this, has, well, I'd say it's budding because there's a lot of work left to do, but I don't think anybody else has quite what we have in terms of describing the world in exact symbolic terms. So we have this thing called the entity framework. This is what powers Wolfram Alpha. So we have these ideas of entities. So I'm just picking some random ones. We have examples. So we have the concepts of different sounds of different minds, like, the type of things that you get coal from. Species reproductive feature, that's an interesting one. Oceans, buildings, organization types, nuclear reactors, genes, food processing types, important people, metropolitan areas, physical activities, all these things. So kind of the basic example I would bring up is just something like elements. So you can access this, the natural language input for accessing the entity framework, the knowledge base, our information about the world we live in, by pressing on a standard QWERTY keyboard, Control equals, and that will bring up this little box. On your keyboard, if you are not using QWERTY, if you're using, I don't know how the Germans pronounce it, but instead of a Y, they have a Z at the end. I always say QWERTZ. It sounds fun. You can go to Insert, and you can do Insert Freeform or Inline Freeform Input, and whatever shortcut appears here, that will be your shortcut to open up this box. And then you can type things like I've done below. So if I type gold, we now know that we're not talking about the string gold, we're talking about the idea of gold, the concept of gold. And because this is a very broad thing to talk about, again, a person, an element, a molecule, an organization type, we just call these entities. They're kind of generally existing people, places, things of this sort, ideas. And from this, because it's not just a string, we can extract worldly information from it, like its density or its atomic mass. Or we could get the area of the city of Houston. We could get Stephen Wolfram's birthday, which was just about 2 weeks ago. Birthplace for the same person. We can say, oh, okay, London, where's London? And then we can compute with these things directly. We can say, oh, okay, there's where London is. But still, this is not a complete way to talk about the world. Like I said, there's more work to do. So in the sentence, I bought 2 pounds of apples, which is a totally reasonable sentence, right? If you really like apples. Wolfram can symbolically represent 2 pounds of apples because we have this idea of a quantity. So for example, quantity 2 pounds. When you have a quantity, by the way, the reason you want a quantity is because then you can do things like talk about it in kilograms, you get an exact conversion there. And we can talk about 2 pounds of apples, and we can even get nutritional information about the 2 pounds of apples, but we don't have a way to really talk about I bought, right? That's like an idea, just like, the cat moved, that semantically makes sense, but it's not something we can represent with our language yet. With a fully complete sense of semantic grammar, you could emulate the behavior of ChatGPT and you could make locally meaningful text, sure, but you could also go a lot further than generating locally meaningful text, that is, text that is locally relevant to your prompt, that makes sense in the context of your prompt. But if you have knowledge about the world, you could ask the model about globally meaningful results. So these things could involve all this information about the world, like about elements or places or people or molecules or nuclear reactors. And it could also involve, with the full power of a computational language, any heavily algorithmic or computational steps that the neural nets that we've been talking about are just not as good at. So ChatGPT so far has pieced together a pretty dang good sense of semantic grammar by looking at all this training data that it's been fed. And that's why it produces sentences which are syntactically and semantically reasonable. But it is the case that sometimes it will get information about the world wrong, and it doesn't have a way to know that. And that's in addition to kind of algorithmic tasks being a little bit elusive for these transformer models. Remember, even the parentheses matching language is a little too hard for a transformer to get right. The computational language would kind of expand on these ideas and let it talk accurately about the world and do computations about the world. So with access to a full computational language with its own way to talk about the world in a sense of a semantic grammar, ChatGPT could have a sense of what's popular based on its training data. Excuse me. It could have a sense of what's popular based on its training data. It could have knowledge about what is and isn't possible based on the computational language part. And it would have immediate access to irreducible computations that neural nets cannot learn, but can only memorize. So the kind of big idea here for all this yapping is that such a system would not just be able to generate reasonable text, but it would be able to work out whether what it's saying is really correct. And that kind of opens the door very significantly to, a lot of possibilities. As if you can ask ChatGPT something and you could be, you could have a good sense that it really knew what it was talking about and that it was really referring to real facts about the world and really talking about real things about what's possible. Or maybe you could prompt it with the text of a book and it could say, oh, okay, well, in this book, I have this sense of what's possible and what's real. You can ask real questions about the world that can get a lot more complex and a lot more, let's say, less soft questions. So a lot of questions you might ask ChatGPT. I don't know how to categorize these things exactly, right? But when you ask ChatGPT something, it's not something that you should believe just outright, and it's not something that looks like a proper full analysis by a fields professional might look like. It's a little bit ad hoc. It's based on kind of probabilistic senses of what's popular based on the training data. It just doesn't have the ability to really know something. If you were to give an LLM like ChatGPT access to a system that can confirm things and that actually knows things, then that's something pretty big, I think. So the question at the end we're left with is, what is ChatGPT doing and why does it work? And here's the little summary section. So after all of this, after all we've been through, hopefully you've gotten kind of a solid picture of the basic concepts that underlie ChatGPT. You start from a massive collection of human-created text. That's from books, websites, transcribed audio and video. Funnily enough, that's also done with neural nets, of course. Then you train a big neural net to generate text that looks like that from the training data. And then what the neural net in particular needs to do is it makes the neural net take a text input and then it continues from that input such that the result looks like, quote unquote, whatever it was trained with. So you give it some text, it comes up with a way to generate a next word that looks like what it thinks language ought to look like. And so for all its emergent complexity, the actual internals are very simple. The neural net itself, just again, like I said above, it converts its text input into numbers. It passes it through a bunch of matrices every time it wants to generate a new next word or token. There are no loops. There's no complex recurrent structure. There's no complicated super graph structure thing going on. You get some numbers, you put them in some matrices, you pass the results through, you're good to go. So, you start with some prompt, The prompt is embedded, broken up into pieces, multiplied by some stuff, multiplied by some more stuff. And then at the end, what you get is the next word. And the surprising thing about all this that we keep pushing is that it really does work to produce human-like text that can contextually respond to new things that people tell it. So when you give it some information in a prompt, you don't have to retrain it. Just like a person, if you're trying to have them help you with something, you can kind of give them the outline of your problem, and they don't have to rewire their entire brain to figure it out, right? They can just take the context of what you have said and use that to help you answer the question. In the end, it still does have flaws. So it can have stuff that, or can produce things that don't make sense in our reality, or that don't correspond to correct computational outputs, because again, the fundamental mode of operation is just to continue text in a way that seems reasonable. And these flaws are pretty human-like. It's not so good at computation, and it kind of just says things that are popular. So again, it's a lot like a human in that way. So if you give access to an LLM, if you give an access, tripping over my words. If you give an LLM like ChatGPT access to computational tools like Wolfram Alpha or Wolfram Language that are both computational tools and have some knowledge about the world, then that can go a long way to shoring up these gaps or flaws in the network. So, and then as far as kind of future directions aside from that, because this is very much a current direction, the fact that we have a simple structure for ChatGPT that really works at all suggests that it could be that there are simpler explicit laws of human language than we might have imagined. One final poll question here before we get to the summary of the talk, which includes a summary, no less. So integration with Wolfram Language allows ChatGPT to do which of the following? Perform algorithmic computations, access factual information about the world, check whether its best guess is actually correct, at least in many cases, or all of the above. And so far, looking pretty one-sided in favor of all of the above. And indeed, that is what I would go with as well. So Wolfram Language kind of has all these features to it, right? Clearly, it can perform algorithmic computations. That was kind of the whole original idea. It can access factual information about the world through the entity framework, just like Wolfram Alpha, right? And it can use this information to check whether what it's saying is actually correct, at least in a lot of cases. And as the language learns more and more about the world, it can allow ChatGPT and other LLMs to better and better check facts about the world when it says them, instead of just kind of saying things that are popular or probable. Okay, so our summary here at the end is that the fundamental architecture and the mathematical operations that underlie ChatGPT are pretty simple, which may suggest that language itself is simpler than was previously imagined, since it can be kind of emulated very accurately by a bunch of linear algebra. And if language is more tractable than previously imagined, it might be possible to derive explicit laws that govern its construction. And those laws could take any shape or any form, and they could appear in any basis or any variable system. But it's possible that maybe they have something to do with how ChatGPT moves from point to point in meaning space. And so ChatGPT, for all of its goodness at discovering implicit laws about syntax and semantics, it is not so good at performing irreducible computations or truly knowing things about the world in a sense of what's true and what's not, versus just what's likely to be true and what's not likely to be true. And so synthesizing ChatGPT with a computational language like Wolfram Language would give it the ability to overcome kind of the most serious flaws that it has. And if you have a system that has access to information about the world and access to general computation, then that system is not just able to kind of answer basic questions about the world, but it can be capable of making like serious real world predictions about things that you might not have been able to synthesize yourself before. So, visual summary as usual. We can emulate the language part of the brain, at least, with a very simple mathematical structure. It might be that there's some sort of sense in this horrible movement through meaning space that we see here. There might be something to it. Hopefully we can extract something explicit about the laws of syntax and semantics from a neural net, but who knows? And this will be the focus of tomorrow's talk. You can imbue ChatGPT with the power to shore up its primary faults by giving it access to a computational language with knowledge about the world, like Wolfram language.